Hi, good morning, everyone. My name is Jason Otkin. I'm a research scientist at the University of Wisconsin-Madison. My co-author on this presentation is Mark Svoboda. He's the director of the National Drought Mitigation Center. In this talk, we're going to provide an overview of some of the tools that have been used to monitor flash drought and describe some of the strengths and weaknesses. This will then lead to a list of challenges, gaps, and needs that have to be addressed in order to effectively monitor flash drought across the United States. So I'm going to start out with a schematic that shows the typical evolution of flash drought from the perspective of vegetation impacts associated with agricultural and ecological drought. To capture the evolution of this type of flash drought, it's necessary to use a multivariate monitoring framework that includes a set of variables depicting anomalies in precipitation, evaporative demand, soil moisture, evapotranspiration, and vegetation health. The schematic shows how a multi-week period of elevated atmospheric demand, along with below normal precipitation, can lead to a series of cascading impacts at the land surface. Now, during the onset phase of a flash drought, soil moisture deficits tend to develop in the topsoil layer first and then penetrate deeper into the soil column. Vegetation can greatly accelerate the depletion of root zone soil moisture due to enhanced evapotranspiration, or ET. Now, though ET may initially increase in response to the elevated evaporative demand, the vegetation will curtail its water usage as soil moisture continues to decrease, and this can then lead to a rapid decrease in ET. Now, once drought conditions become severe, visible signs of moisture stress, such as yellow or curled leaves, can become apparent in the vegetation. And a final point I want to make here is that this sequence of events has to happen rapidly for it to be considered a flash drought event. So to illustrate the importance of using multiple variables for flash drought monitoring, I'm now going to spend a few minutes providing an overview of some of the strengths and weaknesses of different classes of tools that have been used to monitor flash drought events. The first one I'm going to discuss is precipitation. Now, an obvious strength of precipitation-based indices is that precipitation deficits are important drivers of drought. They are also easy to understand and easy to compute. Now, as for weaknesses, you do need to have a long data record of at least several decades in order to obtain reliable results. This becomes especially true for flash drought, where rainfall deficits occurring over only a few weeks can be very important drivers of flash drought. Now, other weaknesses are that precipitation indices do not account for changes in evaporative demand, and any impacts on the land surface can only be inferred. So then there are other indices that depict anomalies in atmospheric evaporative demand, which is another important driver of flash drought development. Evaporative demand is also relatively easy to compute. This can be done using either in situ observations or output from land surface models and reanalysis data sets. Now, like precipitation-based indices, however, there are several notable weaknesses when using indices that are based only on evaporative demand. Now, two of the most important weaknesses are that such indices do not account for precipitation, and they do not provide direct evidence of impacts at the land surface. For example, it's very common for periods of elevated evaporative demand across the eastern United States to actually have increased rainfall because the hotter weather leads to more thunderstorms. Now, this means that indices that look only at evaporative demand can actually have extensive areas of false alarm because the elevated evaporative demand may also be accompanied by heavier rainfall. So another class of indicators focuses on soil moisture, which is a very important drought indicator due to its relationship to vegetation health. Notable strengths of soil moisture-based indices are that they provide a measure that is directly relevant to vegetation health. They can also be computed from a variety of sources, such as in situ and remote sensing observations, or from output from land surface models and reanalysis data sets. Now, weaknesses of these indices include the presence of large spatial heterogeneity in soil properties, which means that observations may only be representative of a small area. They also require detailed knowledge about soil types in order to compute the field capacity and wilting point, which are necessary in order to determine if drought conditions are actually occurring. Now, lastly, in situ sensors can be difficult to install Land surface models can be biased, and satellite retrievals are only sensitive to the uppermost few centimeters of the soil profile. Now, despite these weaknesses, soil moisture is very important for drought monitoring applications. Okay, so the final class of physical indicators I'm going to discuss are those that depict changes in evapotranspiration or in the ratio of the actual to potential ET. Notable strengths of ET-based indicators are that they are a direct measure of vegetation health, with below normal ET strongly correlated to poor vegetation health and to reduced crop yields. ET-based indicators will also respond quickly to rapidly changing conditions and can be computed using remote sensing observations or output from model reanalyses and land surface models. ET-based indicators also have several weaknesses. For example, current versions of satellite-based ET datasets are only available in clear sky areas, which can delay their responsiveness during flash drought. Modeled ET can be heavily parameterized and biased, and in-situ flux tower measurements of ET are very limited. Now, despite these limitations, ET-based indicators are very important because they provide direct evidence of drought impacts at the land surface. Now, as such, they have been used pretty extensively. They've been used in many flash drought studies during the past decade. Now, before moving on to discuss some of the challenges and gaps in existing flash drought monitoring methods, I also want to discuss the U.S. Drought Monitor. Now, notable strengths of the Drought Monitor are that it is impact-based and generated at weekly intervals based on expert analysis of multiple data sets and a feedback from observers in the field. This makes it unique among drought indicators because it combines information from more than one data set. Now, a weakness of the Drought Monitor is that it contains many drought signals because it's designed to depict all types of drought and also contains a subjective component due to human involvement when making the weekly analyses. Now, these aspects then can limit its utility for flash drought monitoring purposes. Okay, so next I want to summarize results from these previous slides, and I'm also discuss some of the challenges that we experience in regard to monitoring the evolution of flash drought. Now, as mentioned earlier, there are many drivers and many impacts during flash drought that together require a large set of tools in order to monitor flash drought from its inception to the end of the rapid intensification period and also beyond that. Now, I want to emphasize again that no single monitoring data set is able to provide a complete representation of flash drought. Instead, it's necessary to use multiple indices that capture different aspects of flash drought. It's also important to use monitoring tools that are able to respond quickly to changing conditions. This sometimes means that you can use existing methods, but only when they are computed over short time intervals appropriate for flash droughts. It's also helpful to use data sets with high spatial resolution so that you can capture local conditions. That typically means using satellite-derived data sets as much as possible because they have very high spatial resolution compared to other data sets. We also need to use data sets with a reasonably long period of record so that you can have a proper understanding of what is normal for a given location and time of the year in order to determine whether or not the rate of intensification that you're seeing is truly more rapid than normal. A final point I want to make here is that in the context of operational applications in drought early warning systems, it's also important to minimize data latency as much as possible because data lags can delay drought mitigation efforts. This is also relevant for the NIDIS drought early warning systems where the spatial and temporal resolutions of those systems need to be increased as much as possible in order to provide early warning of flash drought development. Now, regardless of which data sets are used to monitor flash drought, a key thing is that we need to agree on a general framework for what flash drought is because how we define it impacts how we monitor and forecast them. We also need to better understand where and when each metric is most useful for depicting flash drought. Again, the emphasis here is that we need to use more than one data set to monitor flash drought, but to use them effectively, we also need to know when and where they work best. Now, this takes an honest appraisal of their strengths and weaknesses because there is no single data set that can capture all aspects of flash drought. For example, atmospheric drivers such as precipitation and evaporative demand don't provide any direct evidence about impacts, which are key for drought, but they can provide very useful early warning. A final point is that all studies have focused on soil moisture or vegetation flash drought, but there's no reason why the flash drought terminology can't also be applied to other types of drought, such as hydrological drought. Okay, so I'd like to end with a couple final thoughts. First, it's critically important to look at changes in the index rather than just the current value of the index, because the key characteristic of flash drought is its rapid rate of intensification. If you only look at the current value of a given index and not at how that variable has been changing with time, then you can't identify flash drought because you're missing the time change component of it. Also, it's important to account not only for the flash part of the definition, but also the drought part, so that you can include the impacts caused by flash drought. So finally, I'll reiterate here that like all types of drought, impacts are a key feature of flash drought, which means that flash drought monitors need to include impact-based indices such as soil moisture and ET, in addition to indices that depict the meteorological drivers of flash drought. This framework is consistent with the flash drought definition that was added to the AMS glossary last year. So with that, I'll stop here. Thank you for your attention.